I want us to just talk a little bit about the hydrolysis of esters, amides, and nitriles. I've already done the mechanism of the hydrolysis of esters, but just to remind you that when we have an ester, the hydrolysis of an ester would typically take place under basic conditions. So this is the base hydrolysis that we're going to be looking at these things. So if we did a base hydrolysis of esters, what we ended up with was the carboxylate salt, so O minus, and then we have the counter-ion, the sodium, we'll just write it like that, plus the alcohol for the other group. So this would be R prime OH. So if we look at that, this part over here is our alcohol, and the other part over here was our ester, or became our carboxylate, which is that over there. So that part we can do mechanistically, but we can extend this and we can do the mechanisms of them. I'm not going to do them in any detail now, but we can certainly go and do that, look in your textbook. But we also need to look at what happens when we have an amide. So I'm just going to take a very simple example of an amide over here. This is just a primary amide. It's an amine. The equivalent here, of course, is that instead of this OR over there, we have an NH2. Now, it might not be an NH2. It could actually be some R groups. In fact, I'll just change that H into two different R groups like that over there. So under the same conditions, we can hydrolyze amides using sodium hydroxide. And if we use the sodium hydroxide, we end up with exactly the same sort of pattern. So we end up with the carboxylate like that. And in this case, at the end, we're going to end up with an amine, which will be an NH like that over there. So here is the amine part, and the carboxylate is exactly the same as before. Now, I'm not going to look at the mechanism in full detail. The principles behind this are exactly the same as what we had with the esters. But just as a form of reminder that when the hydroxide that was there sort of kicked in, so it acted as a nucleophile and it added to the carbonyl carbon, because that's the electrophilic position, we get this classical movement of electrons where the nucleophile, in this case the hydroxide, adds to the carbon, we break the pi bond, and we end up with an O minus. So the intermediate that we get would look something like this. We have an O minus, we've added our OH, and we've got our amide RN2, something that looks like that over there. Now, this particular intermediate presents a little bit more of a unique but different experience as to what we had in the case of esters, and it explains why amides are actually much harder to hydrolyze than esters are. Esters, we do typically heat them up when we do this sort of hydrolysis, but amides we have to heat up for a much longer period, and we really have to cook these reactions in order for this to happen. And the reason being is in the next step. You see, we can predict what needs to happen over here. We can take this negative charge and we kick it back in. And at this point, something has to break. We have to break either this carbon-oxygen bond over there or this carbon-nitrogen bond over there. And clearly, for the reaction's sake, what actually happens is that movement of electrons over there. Well, I mean, you can push those electrons. You can say, okay, well, that happens. It's all very well. However, the point is, why did this break and not this one over there? And that's actually a very good question, because you see, this bond over here is actually the weaker bond. If we're going to break any bond between these two, it's actually this bond which is going to want to break, because what's going to leave is hydroxide, an O minus. Whereas when this breaks over here, what's leaving is an N minus, which is a much stronger base. In fact, this step over here is not favored at all. There's only one reason that this works, and it's the same reason why the hydrolysis of esters works. And that is that once this leaves, we end up with the carboxylic acid, and the N minus that leaves is a very strong base which can deprotonate this acid, and that pushes the reaction to being irreversible. Once we get to this step over here, the reaction is irreversible. So this step is the mechanism, and it gets us to the product that we need to be, but we need to remember that actually this is a terrible, out of the two options that are there, this is not a great one for the leading group. And it only works because a very small amount of that, when that happens, and a very small amount forms, we are able to then form the product because that N- that forms can immediately deprotonate in exactly the same way as hydrolysis of an ester under basic conditions is very efficient. The last thing we need to look at just in this kind of introduction part here is the hydrolysis of a nitrile. And when we hydrolyze nitriles under, these are actually a little bit more tricky. And we use a strong base such as sodium hydroxide. Remember, we can use any base, any hydroxide. It could be lithium, potassium, or sodium. When we do this, we also get the carboxylic acid, or the carboxylate, I should say, and we end up, in this case, we're going to end up with ammonia, NH3. So now the question with this one is a little bit like, okay, well, how's this all happening? Because where's all this occurring from? Well, the mechanism of this is actually very similar to that of the amide. In fact, the amide is the intermediate. So if I draw this out again, a nitrile is actually a triple bond. So this part over here, I'm just going to color that in. This is the part that's actually going to be the leaving part, which ends up over here. This carbon is going to be become our carboxylate. And so when we have an O-, it's going to kick into this carbon, which is also electrophilic for exactly the same sorts of ways. It's almost like a nitrogen equivalent of carbonyl, but not quite, because it's 3 bonds instead of 2. But it is electrophilic in exactly the same sort of way. And so we can get this intermediate being formed over here. So it's we've got our carbon, which now has its OH on. Now we've got a double bond to nitrogen, but the nitrogen, of course, now is negatively charged. Like that. All right, so an N- is not great at all. An N- is not something that wants to remain that way. And you can go and look at the full mechanism of this, but essentially we're going to get a proton transfer. This proton is going to end up on that nitrogen. It obviously needs to happen from the nitrogen picking up the proton, like that. And then we can also, let me just draw that out. So we end up with a nitrogen with an H on it, and so now we've got an O-, like that. And now what we have here is an imine, and the imine can kick its electrons in like that. This is just a resonance form of that, so we could draw it out as a resonance form, and we end up with this, which is effectively just, we're halfway there to what we had before with the amide. This is, if we just protonate that, we've got an amide, and then we just follow the same mechanism that we had over here for the amide. It just has to happen again. So when we hydrolyze a nitrile, we actually need 2 equivalents of hydroxide in order to do that. So, because we've actually introduced 2 oxygens over there. So if you calculate it all out, you'll figure out that that's important. You'll also notice that we also need some extra hydrogens at the end of this. That'll come from like the water that will be present in the hydroxide. So now we come to the question, which is, well, what about using something else? By something else, I mean instead of hydroxide. So if we're to hydrolyze an ester, so we've got our little example of our ester over here. So here's our so-called leaving group part of the ester that's going to leave and form that alcohol. Under normal circumstances, we were using an OH, and so the negative charge of the oxygen attacked over there. But what if we were using not just an OH, but some other kind of nucleophile? And we'll give it a negative charge on here because we need something kind of stronger to react with an ester. It won't be, neutral molecules are a little bit challenging, not always, and we'll see an example now, but for now we'll just put a negative charge over there. And if we had something else than hydroxide, then what might occur in this reaction is we might get something as a product that looks like this. And we're going to end up with this O- over there. So what we've done is we've essentially just used a nucleophile, something else, and we put it over there. In the previous example, the nucleophile was hydroxide, and that's what ended up over there. Of course, the hydroxide formed a carboxylic acid, and so this deprotonated the carboxylic acid, and we ended up with a carboxylate. The question is can we use something like that? And the answer to that is absolutely yes. There's a whole range of different things that we can use. And the first example that I want to look at is where the nucleophile is another alcohol. So now I'm going to use another alcohol, or another alkoxide, I should rather say. And so we've got R prime. Let's make this R double prime. So this is a different type of alkoxide to the one that we had over there. This one, for instance, could have been a methyl group. So this would have been a methyl ester. And maybe this R2 over here is an ethyl group. So it would have been an ethyl group. We're going to be making an ethyl ester. So mechanistically, we've got this new alkoxide that's being added as a nucleophile going in. And so what happens is we do our standard set of reactions. The first step is the lone pair. And this negative charge will add to the carbonyl. We break the pi bond. And by now, I'm hoping that we are satisfied that we get that tetrahedral intermediate, which is extremely important. And that tetrahedral intermediate will then collapse again. And so sometimes take the shortcut of showing these two arrows happening at the same time. And we can then lose our leaving group. And that will be the product that we'd form over there. So now we would end up with a new ester like this. So we call it double prime plus our alkoxide that left at the end. And we'd end up with something that looks a bit like that. Great. This is now quite an excellent way of changing one ester for another ester. And this type of reaction is called transesterification. And this is a great way of switching out one ester for another. It actually turns out to be something that's more of a problem in reactions, because I think the more astute of you who are listening to this might be asking yourself the question, hang on a second, if this OR double prime does a transesterification to form that, why can't this OR single prime do exactly the reverse reaction and go back to that over there? And that is exactly the problem with this reaction. We can definitely go back to the starting material like that. And so in order to do a transesterification correctly, we have to use the principles of Le Chatelier in order for this to happen. So a practical example of doing something like this, where this would work, is say, for instance, we've got some ester, and it is sitting with, maybe it's a bit of a boring ester. It's a methyl ester, and we don't really want the methyl ester anymore for whatever reason. Highly unlikely, but anyway. What we want to do is we rather want an ethyl ester. So what we want to do is we want that to act as the nucleophile so that we can do the transesterification and end up with an ethyl ester. Now that reaction is certainly going to work, but it's not going to give us a very good yield of this, because the problem that we have is that if we just have this over here, we need to push this equilibrium that's going to form, because methoxide is going to form on this side over here. That's the other part, that left. So there's our green and green. And because it's left, we need to have some way of pushing this reaction all the way to completion. And one way to do it is to basically have a huge amount of this. Now remember, this equilibrium is a 1-to-1. So if we've got 10 equivalents of this, we're then going to push this equilibrium to something more like, 10-to-1. If we have 100 of these, then we're going to start getting a lot more of that. That could be quite wasteful in terms of reagents. But one way of doing it is just recognizing that if we did this reaction in ethanol, if we're doing this as a solvent, using ethanol as a solvent, there's going to be a huge excess of ethanol that is present. And when the methoxide forms over there, some of this methoxide in a 1-to-1 reaction is going to disproportionate and form ethoxide. We're going to kick that off and we're going to generate some more ethoxide. And so just by doing this reaction in ethanol, we can have one equivalent of ethoxide. We can have lots and lots of this. And essentially, we've effectively got a whole lot more of ethoxide present. And so this transesterification esterification reaction will work. It's not a particularly useful reaction. Some cases, there are places where people do need to do this, but this is the type of thing that tends to happen. There is a more important reaction that occurs on esters where we use a beta nucleophile, and that is a reaction which is called Ammonolysis, where the nucleophile is an amine. Let's look at that now. All right, so now I'm going to look at ammonolysis. And ammonolysis, its name means aminolysis. It is the breaking of bonds using an amine group. And so this is the type of reaction that is going to occur here. We're going to use just a neutral amine to react with the ester. So in the past, we were looking at O minuses as nice, strong nucleophiles that can add to an ester. But an amine nitrogen, its lone pairs are actually strong enough to react with the ester and to form the product, which in all cases ends up being an amide. So let's just draw the product out so we can see it, and then we'll have a look quickly at the mechanism and follow the principles of how these reactions occur. And hopefully we'll start to recognize that the same thing is happening over and over again in all these reactions. All right, so just so we can follow things, here is the amine part, and we're going to see now that that H over there actually came from the amine, and this is the OR bit for the alcohol that was expelled at the end. But this, if we follow the mechanism now, we're going to see that a lot of the principles of acids and base chemistry and mechanistic thinking are going to come up over and over again. So it's the same principle here. When we've got a nucleophile that is good enough, it can add to the carbon-al-carbon, and we give out the lone pair, we break the pi bond, and it is able to form our tetrahedral intermediate, which is quite important. So this, of course, is an equilibrium. It can go both ways, and we get this tetrahedral intermediate. So we have an O minus over there. We've got the nitrogen with the R prime on it, and it actually has two hydrogens on, and this is something that a lot of people forget when they first do these types of reactions, is that they forget that there were two hydrogens over there when this first reaction happened, so we have two hydrogens there as well, meaning that this is now an ammonium, not an amine. We just color things in so we can see where everything is. What's going to happen now is if we look at this intermediate that's formed, the tetrahedral intermediate, it is unstable and it wants to collapse. It has one option. One option, of course, is this O minus can kick back in. And then it's got two options. What's it going to do? Is it going to kick out this nitrogen, or is it going to kick out this oxygen over here? And at this point over here, the case is very clear. It must kick out this over here. This ammonium has a pKa of 11. This O minus would have a pKa of 16, the protonate form of them. And so what's been kicked out is a much weaker base than this that would be kicked out over here. So if this had to come back in, this must leave. That's the equilibrium reaction which sends us back over there. However, what we do have in this tetrahedral intermediate, and all very close to each other, is you've got an O minus, which is an extremely strong base, which is very near to an ammonium, which has a pKa of 11. So we've got the 1611, big difference in pKa values. And so this O minus is absolutely going to want to pick up one of those H's, and we're going to form our next, it's still a tetrahedral intermediate, but the next part, which we can then see what happens. So we now have neutralized everything. So we've got our R double prime, we've got our H over there, so this is sort of an amine part, and we've got the OR prime over there. Okay, so everything has been neutralized, and now what we need to do is we need to say, okay, what's going to happen now? What's going to kick in to collapse that tetrahedral intermediate? Because it doesn't want to stay like that. That's an unstable form. How do we get back to this over here? Now, I haven't left a lot of space here, so I'm going to have to do my next step down here. But the point is here is that we want to get this to go away. So we're going to kick out an O minus. So the O minus is going to want to leave. The question is how does that O minus leave? Now, and why, of course, does that O minus leave? Now, we've got three heteroatoms over here. We've got lone pairs on this oxygen, and those lone pairs could kick in. And then we could kick out an N minus. Very, very bad idea. Too strong a base, never going to happen. Or we can kick out an O minus. Not great, but it's better than kicking out an N minus. Or we've got a lone pair of electrons on the nitrogen, which could kick in. In that case, it could kick out this OH over there, or it could kick out the ester part, OR, out on that way over there. And that both of those would be O minuses, and they'd both be essentially equal. And both of those could happen. Now, the question that actually we have to think about is, we've got two oxygens and one nitrogen. Which lone pair is the lone pair that is going to kick in to kick out and break one of these bonds over here? And the answer must be the nitrogen lone pair, because the nitrogen lone pair is the more nucleophilic, more active, more lone pair that is willing to be involved in resonance. So it is going to kick in like that. And now we have to decide what happens. Which one are we going to kick out? Now, there's a 50-50 choice between these two over here. If we kick out this one, and you should go and test for yourself, if we kick out the OH, what we're going to find is that we're going to get to a point where we're stuck, and that the intermediate that's going to form is not going to be an amide. It's going to be something else, which is not particularly stable. So even though it could form like that, it's probably just going to come back again. So what actually happens is we're going to kick out the ester, and that ends up giving us the OH is still there. We made a double bond now to the nitrogen. We've got the R, double prime, and we've got that H that's remained at that point over there. And we also kicked out the OR prime minus. Okay, so now if we look at that, this, and I've forgotten something, which is the positive charge on the nitrogen. This is almost at the amide stage over there. In fact, it's a protonated form of an amide. In fact, when amides get protonated, the nitrogen doesn't go, the proton doesn't go to the nitrogen, it actually goes to the oxygen because of this lone pair of electrons that kicks in and picks up the hydrogen there. So all we need to do now is we need to take our now strong base, the alkoxide, and this electrons will kick back in like that, and we end up with, when we follow that, we'll end up the amide that has been formed over there. The key here is to look at the principles that come up in this type of reaction. What we have looked at overall is reactions involving esters, essentially. We also looked at briefly at amides being hydrolyzed, but essentially we've looked at some kind of ester. This part over here has been the leaving group in all cases. And we've looked at nucleophiles. The most simple of the nucleophiles was, of course, the OH minus. The other one was if we had to use some sort of ester, and now we've looked at what happens if we use an amine of some form. So I'm just going to take a primary amine like this as an example. But those are the three types of nucleophiles that we've used to react, and all of them have followed exactly the same principles. The key here is to watch what happens in the mechanism at each stage and think about the different options that might occur and why they do and they don't occur. And they all follow that sort of acid-base question in terms of the leaving group. When it leaves, is it a good leaving group, and can that reaction kind of follow through? And so one of the difficulties that we saw, for instance, when this wasn't an ester, if it's an amide, the amide is a very, very bad leaving group, and so that made that reaction a lot slower and more difficult. And we only worked in terms of at the end, because that N minus that was kicked out could deprotonate to get the carboxylate. So that's why that reaction worked.